Hello. Today we are going to discuss the second part of rooted trees. This is chapter 10, Theory of Graphs and Trees, section 10.5, Rooted Trees. Let's discuss the second part of the section. Uh, we discussed binary trees in the last class. If I give you summary of binary trees. Binary trees are the trees those are having maximum two children for parents. It's something like this. A binary tree is something like this. For each parent, there are at most two children. At most two children. This is a binary tree. Sometimes it might have one child too. Something like that. So one child case, another one child case. Okay, so this is a binary tree. It can have maximum two children. Okay, so this is a binary tree. Okay, so let me give another example where it is not a binary tree. This is not a binary tree. All right. All right. You know about binary trees now. Let me take this right here. All right. Let me read this. An interesting theorem about full binary tree. This is a full binary tree. If it's a full binary tree, then that means each parent has two children. Each parent has exactly two children. Okay, something like this. If it's a full binary tree, it goes like this. Each parent has two children. Exactly two children. This is a full binary tree. All right. Now you know about binary trees, full binary trees, and not binary trees. So let me rearrange this a little bit. All right. An interesting theorem about full binary tree says that if you know the number of internal vertices of a full binary tree, then you can calculate both the total number of vertices and the number of leaves. There are two conditions here. There are two things that you can compute. The first thing is total number of vertices, and then the number of leaves. All right. What you have to know here is, early you have to know that a number of internal vertices. If you know number of internal vertices, then you can get these two information. All right. Once you know the number of internal vertices. Okay. Theorem 10.5.1. If k is a positive integer and t is a full binary tree, that's important. It should be a full binary tree. with k internal vertices, this information is required. K internal vertices, then the first condition says T has total 2k plus 1 vertices, and then T has k plus 1 leaves. Okay, 2k plus 1 vertices and k plus 1 leaves. All right. In the next slide, we are going to prove this theorem. Before proving that, let me explain one example here. Let's consider this tree. It should be a full binary tree. All right, it should be a full binary tree. And then it has k internal vertices. Let's count how many internal vertices. 1, 2, 3, 4, 5. There are 5 internal vertices. Okay. Number of internal vertices, that means k equals 5 here. All right. According to the theorem, according to the theorem, a number of vertices should be 2k plus 1. That means 2 times 5 plus 1. Which is 11. Number of leaves equals k plus 1, which is 5 plus 1, 6. Okay, let me count them. Let me count the total number of vertices. All right, for that I use green color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 11, right? So that is this number. The number of leaves, I'm going to use orange color to count leaves. 1, 2, 3, 4, 5, 6. Right? That's 6. So this theorem is true. By using this example, you can understand this theorem is true. But since it's a theorem, you have to prove. You have to provide a mathematical proof for that. So in the next slide, we're going to provide a mathematical proof for this theorem. All right. So let me work on that. This is an example that we can use to check whether what is explained by this theorem. Okay, that example explains what is meant by this theorem. Okay, so the proof. First, we are going to show that this tree has 2k plus 1 vertices. All right. This says you can just partition vertices into 2 disjoint subsets. All right. Let's take a tree, and then you can categorize these vertices into 2 groups. So the first group is vertices that have parent, right? So that's the first group. And the other group is vertices that do not have parents. Okay, so vertices of T can be partitioned into 2 disjoint subsets. So those are the subsets. Take any tree you want, and then this categorization is true. So you can just do this categorization for any graph, any tree. Okay, so which are the vertices which have parents? So this has parent, that has parent, that has parent, that has parent, has parent, has parent, has parent, has parent, has parent, has parent. Okay, these are having parents. The only vertex that do not have parent is this. Okay, so because of that reason, let me mark this by that color. Vertices that have parents. Alright, so these are the vertices having parents, which are colored in light blue, and orange is used to show vertices do not have parents. Okay, so these are the two disjoint sets. These are the two disjoint sets. Let me use a different color for that too. Alright, now it's meaningful. Alright, good. Alright, now it is given right here. The total number of vertices equals number of vertices that have parent, the number of vertices that do not have parents. Alright. Since it has k internal vertices, that is given to you. In the previous slide, I mentioned that it has k internal vertices. It's right here. See, k internal vertices. Now you can just find number of vertices that have parents in terms of k. Now you can find number of vertices, those who are having parents, as a function of k. Okay, so let me consider this again. This vertex has parents, that 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 has. All these are having parents. All right. All those are having parents. Actually, in that case, each internal vertex has parents. You can understand that. This is an internal vertex which has parents, which has children. So this is an internal vertex which has children. Internal vertex which has children. This is not an internal vertex. This is an internal vertex which has parents, which has children. Okay, all the internal vertices are having children. Internal vertex having children. All right. So then, number of vertices that have parents equal 2 times the internal vertices. Okay, it is actually 2 times the k is internal vertices. K is number of internal vertices. K is number of internal vertices. All right, so that is k, and then the number of vertices that have parents is actually 2 times k, because each internal vertex has 2 children. All right, each internal vertex has two children. Let me mark here, and then each internal vertex has 2 children. All right, that is number of vertices that have internal vertices is 2k. All right. Good. Now you have to find how many number of vertices that do not have parents. In this tree, there's only one vertex which does not have parents. That is the root. Okay, it's only the root. Root doesn't have parents, so it is just one. Okay, it is just one. This is only the root doesn't have parents. All right. Now the answer is 2 plus k, which is right here. Okay, the total number of vertices is number of vertices that have parents, which is 2 times k, and number of vertices that do not have parents, which is 1. So the total number of vertices is just 2k plus 1. Okay, so that is clear to everybody. And then let's go to the next slide. In the next slide, we are going to show T has total k plus 1 leaves. All right, for that, what we do, we just write down this equation. The total number of vertices can also be written down as number of internal vertices and number of leaves. Okay, that's another formula. The total number of vertices equals the number of internal vertices plus number of leaves. If I use the same diagram to show that, that means the same tree to show that. Oh, sorry. I just need to delete this. That's all right. I can just. Why don't I redraw this? One vertex here. 2 vertices there. Here I have the same tree. Now let me mark number of internal vertices. This is an internal vertex, internal vertex, internal vertex, internal vertex, internal vertex. These are the internal vertices, and then just let me mark the leaves. Leaf, 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 leaf. Okay, there are 1, 2, 3, 4, 5 leaves, and then 1, 2, 3, 4, 5 internal vertices. Oh, I'm sorry, I forgot that. This is a leaf too. Okay, so these are the leaves, and others are the internal vertices. All right. In this problem, you know, there are k internal vertices. This is given to you. You know this. Okay, that's what you know already. And the total number of vertices for this for such a tree is just 2k plus 1. You got this one from the previous part. From the previous part you learn total number of vertices equals 2k plus 1. And you know it has k internal vertices, which is right here. And then what you have to find is number of leaves. Now this is a simple equation you can solve. You just solve this equation, which is 2k plus 1 minus k equals k plus 1, which is right here. Alright, so that is clear. Okay, this gives total number of leaves. Okay, that's the end of the proof. Let me go to the next slide. Is there a full binary tree that has 10 internal vertices and 13 terminal vertices? Terminal vertices are leaves. Okay, terminal vertices means leaves. Alright, we can just check whether this is true or false. Okay, for that we could use theorem number 10.5.1. By theorem 10.5.1. A full binary tree with 10 internal vertices has how many total vertices? Has number 1, it has 2k plus 1 total vertices. Okay, if it is k, you have 2k plus 1 total vertices. You can take this as k. And then it has k plus 1 terminal vertices. It has k plus 1 terminal vertices. That has 10 plus 1. That means k plus 1. K plus 1 terminal vertices. It has 10 plus 1 terminal vertices. Okay, that means 11 terminal vertices. It says 13 terminal vertices, which is not true. Okay, there's no such tree which has 10 internal vertices and 13 terminal vertices. Then the answer is no. Answer is no. There's no such a tree. Let me write like there's no such a tree. There's no such a tree. All right. Go to the next slide. Another interesting theorem about binary trace is specifies the maximum number of leaves of a binary tree of a given height. Now we are going to talk about maximum number of leaves with respect to the height. Okay, with respect to the height. Specifically, the maximum number of leaves of a binary tree of height h is this. Okay, the maximum number of leaves of a binary tree of height h is 2 to the power h. Alright, so let's consider t as number of leaves. Let me consider t as number of leaves. Then this t should be less than or equal to 2 to the power h. Okay, which is right here. The total number of leaves should be less than or equal to 2 times h, where h is the height of the tree. Okay, let me take an example and show you this. Now I'm gonna draw a binary tree. You could draw any type of binary tree. This is a binary tree. Let me find the height of this tree. This is level 0, 1, 2, 3. Height is 3. That means h equals 3. Alright. And number of leaves of these tree, number of leaves equals 1, 2, 3, which is 3. You can see that t less than or equal to 2 to the power h, that means 3 less than or equal to 2 to the power 3, which is 8, right? 3 less than 8, so this is true. Okay, this condition is satisfied for that theorem, for that tree. This theorem is satisfied for that tree, that is specific tree we have chosen. All right, so this is the condition. T should be less than or equal to 2 to the power h. Now what I'm going to do is I'm going to get logarithms of both sides of this inequality. Take the logarithm of the left side, then it will be log to the base 2 of t, then this is log to the base 2 to the power h. And this equals, you can take the power in front. You have learned this in calculus 1. So you write this as h log 2 to the base 2. And then you know log 2 to the base 2 is just 1. So this is just h. Because you know this is that. Okay, that means log of t to the base 2 is less than or equal to h. Okay, that condition is given right here. Okay, which is right here. And the second condition tells that the height of the tree is greater than or equal to log 2 of t. T is the number of leaves of the tree. All right. So you are clear about that now. This is theorem 10.5.2. Now let's move to the next slide where we are going to discuss an example. Is there a binary tree that has height 5 and 38 leaves? Okay, height is 5 which is H, and 38 leaves, that means T is 38. All right. Then by the theorem you could write by theorem, I'm sorry. By theorem 10.5.2, any binary tree T with height 5 and with height 5 has at most 2 to the power 5. That means 2 to the power 5 is 2 times 2 times 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 leaves. Okay, it has 32 leaves. That is the most number of leaves. That is 38 leaves is impossible. That is 38 leaves is impossible. All right. The answer is no. There's no such a tree. Alright, so that is the answer. Let's move to the next slide. Alright, this is a corollary. The number of the corollary is 10.5.3. Let me read it first. A full binary tree of height h, in which all the leaves have the same level. All the leaves have the same level has 2 to the power h leaves. At the previous time, in the previous theorem, we said number of leaves should be less than or equal to 2 to the power h. Now we say number of leaves equals 2 to the power h. What is different here is, in this case, all the leaves should have same level. All the leaves should have the same level. That means something like this. All the leaves should have the same level. Alright, it's a full binary tree. It's like something like this. That means the tree should always be symmetric. Okay, the tree is always symmetric. Let me redraw it. I have to expand that a little bit. This is a binary tree. This is a very special type of binary tree. That binary tree has the same level for all the leaves. Each leaf of this binary tree has the same level. All right, so that's a symmetric binary tree. We could say symmetric binary. It's a full binary tree. Each parent has two children. That means a full binary tree. All right, so this has all the leaves has the same number of same level. Now just count how many leaves. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 leaves. Now just compute the height. 0, level 1, level 2, level 3. So the height is 3. That means h equals 3. 2 to the power 3 equals 8. That is number of leaves. Okay, you have seen that. This equals number of leaves. Two to the power 3. Alright, number of leaves equals 2 to the power 3. Alright, so now this is very important. You understand that this is a very important corollary. This corollary holds for the trees which are full binary trees, and then all the leaves have the same level. Okay, now we go forward. Now we are going to talk about binary search tree. Since there are a lot of computer science students in this class, they are familiar with binary search trees. Binary search trees are very convenient in many cases. Now we are going to learn binary search trees. You can use binary search trees to order a set of observations, and then you could sometimes detect anomalies. You can do clustering by using binary search trees. There are plenty of applications of binary search trees. All right, so this is a binary search tree. A binary search tree is kind of a binary tree in which data records such as customer information can be stored, searched, and processed very efficiently. Okay. To place records into a binary search tree, it must be possible to arrange them in total order. You can arrange them in order. All right. Arrange them in total order. That means you can just sort a given set of elements. In case they do not have a natural total order of their own, an element of a total ordered set, such as a number or a word, and call a key, may be added to each record. Sometimes the data have natural order, sometimes they do not have natural order. Okay, if you consider data, some of them have natural order. Like scores, example, scores for an exam. Let's say for an exam. They have order, right? Scores have an order. And then sometimes data do not have natural order. Example, like colors. colors, they do not have a natural order. If they have a natural order, then you can freely order them, or maybe sort them. If they do not have a natural order, then you have to assign an order for them, which is called a key. Okay, let me rearrange this. For this case, we don't need a key. No need for a new key. Here a new key is required. All right. In the second case, a new key is required. That is what explained here. That is what is explained here. If they do not have a natural order, then you have to assign an order for the given observations. All right. The keys are inserted into the vertices of the tree and provide access to the record to which they are attached. All right. Since you provide a key for a set of numbers which are not naturally ordered, then you can refer the numbers by the key. Okay, then you can refer the numbers by the key. Here, let's say the scores 70, 80, 35, 90. So these are the scores of 4 students in the class. Okay, here the colors, you have blue, red, green, yellow. Now we assign numbers for each color. Now this is the key. So we use 1 here, we use 2 for that, we use 3 for that, we use 4 for that. All right, so now we assign a key. Key can be used to call any color in this list. Okay, now go down. A binary search tree has the following properties. The first property, for every internal vertex V, all the keys in the left subtree of V are less than the key in V. Okay, so let me refer that to this tree. Here you have a binary search tree. It has 15 here, and 19 is greater than 15, so we put 19 in the right hand side. 10 is less than 15, we just put 10 here. And then 12 is greater than 10, so we put it right side. 4 less than 10, we put in the left side. I will explain how to make this tree later. And then 25 is greater than 19, so we just put that in the right side of the 19. Okay, so I will explain how to make this tree later. All right, so these are the properties. There are 2 main properties. For every internal vertex V, all the keys in the left subtree of V are less than the key in V. Okay, if you consider left subtree, so this is the left subtree of 15. They all less than 15. All right, keep that in mind. That is number one. And then number two, all the keys in the right subtree of V are greater than the key in V. So as an example, you could consider this subtree. This is right subtree of 15. They all greater than 15. All right, which is given in 2. Let me mark them in colors. This is the green case. That is the red case. All right, for example, check the following is a binary search tree for the set of records with the following keys: 15, 10, 19, 25, 12, 4. You have to check whether that's a binary search tree. You have to check whether it's a binary search tree. All right, that means you have to consider these two. You have to consider these two properties. You have to check these two properties. The first property is for every internal vertex V, all the keys in the left subtree of V are less than the key in V. All the keys in the right subtree of V are greater than the key in V. Okay, so you have to check subtrees and check. We have already taken this subtree and we check that everything in this subtree is less than 15. And then we took this subtree and check all the elements here are greater than 15. And then you have to use this subtree. This is also a subtree, even though it's one element, it's a subtree of 19. All right, so you have to check whether this 25 is greater than 19. That's true. All right, then take this subtree of 10, which is smaller than 10. That's why it is in the left side. And then take this subtree, which is greater than 10. That's why it is in the right hand side. All right, so we checked everything. So this is a binary search tree. All right, so you have to consider these two conditions, properties, and check them. All right, go to the next slide. To build a binary search tree, start by making a root and insert a key into it. First, you have to make the root of a binary tree. Okay, first you have to make the root. In the previous case, 15 was the root. Okay, you have made 15 as the root. That's the first element. You can take that as the first element in the list. Then you make the root. Then second point, to add a new key, compare it to the key at the root. If the new key is less than the key at the root, give the root the left child and insert the new key into it. Now you have to add 10. Let's say you are adding 10 into this tree. All right, now 10. 10 is smaller than 15, so you just put 10 here. Okay. If the key is greater than the key at the root, then give the root a right child. Now let me consider 19. If you're going to add 19 here, so the 19 is greater than 15, that should go here. Okay, so let me mark them. Let me use 3 different colors. So that is that, which is this. This is this, which is that. that is that, which is that. All right, you can keep on doing that. And the next point, after the first couple of keys have been added to the root, and the other vertices may already have left and right children. Okay, so now 15 has left and right children, which left children is 10, the right children is 19. Okay, now we have to keep on adding. So to add the key at the subsequent stage, work down the tree to find a place to put the new key. Starting at the root, we always starting at the root, and either moving to left or right, depending on whether the new key is less or greater. Depending on the new key is less or greater than the key at the vertex to which it is currently being compared. Okay, you have to keep this going. As an example, if you are going to add 12, you could just start from here. 12 is less than 15, you could go that way, and 12 is greater than 10, you could go this way. All right. That is, give me a second. That is given right here. That's how you add 12. All right, let's move to the next slide. In the next slide, you have the binary search algorithm. Since there are a lot of computer science students in this class, I would like to give you this. I don't need to explain this because this is something very easy. We have learned this algorithm right here. So this is the algorithm in terms of words. That's the algorithm. Here the syntax of that. All right, here you have the syntax of the algorithm that I gave you right here. So this is actually the algorithm with words, and this is the syntax, the way you code that on a software. All right, so you can read this algorithm. Now we are going to discuss another example. Go through the steps to build a binary search tree for the keys 15, 10, 19, 25, 12, and 4, and insert the keys in order in which they are listed. For simplicity, use the same names for the vertices and their associated keys. All right, so these are the keys, the list of keys given to you. Now you have to just put them in a binary search tree. Start from the beginning. Step number 1, you have to put the root, which is 15, the first element. All right, you added that 15, and now you have 15. Now you have to add 10. Compare 10 with 15. Since 10 is smaller than 15 and 15 does not have children, 15 does not have the left child, make 10 the left child of 15 and add an edge joining 15 and 10. So you put 10 here and then add an edge. Okay, so that's the step number 2. First case, second case. And the third case, you have 15 here, you have 10 there, and then you have to take 19. All right, 19 is greater than 15, and 15 does not have a right child, so you make 19 the right child of 15. All right, now go to the next step. You have 15 here, you have 10 here, you have 19 here. All right, now you take 15. Next one is, next one is 25, right? So you take 25, you compare 25 with 15, which is the root. 25 is greater than 15. 15 has the right child, which is already 19. Then compare 25 with 19. You check 25 with this. You compare 25 with that, which is 25 is greater than 15. Then move to 19. Then check 25 with 19. Since 25 is greater than 19 and 19 does not have the right child, make 25 the right child of 19. All right. So now we make 25 as the right child of 19. Okay, let's move to the next step. We have 15 here. We have 10 here. 19 there. 25 here. The next element is 12. You have to compare 12 with 15. You compare 12 with 15 and then you see 12 is less than 15, so you move down like that. Since 12 is less than 15 and 15 has a left child, namely 10, compare 12 with 10. Now you compare 12 with 10. Since 12 is greater than 10 and 10 does not have a right child, make 12 the right child of 10. We make this 12 as the right child of 10. Alright, so that is the tree now. Okay, just go to the last step. In the last step, we're gonna bring 4, which is the last element. 4, compare 4 with 15. You compare 4 with 15. Let me draw it here. And let me delete that. Now we already have 15 here, and we have 10 here, 19 here, 12 there, 25 there, and now we're gonna add 4. Alright, we compare 4 with 15. 4 is less than 15 and 15 has a left child, namely 10. Then you go down and then you compare 10 with 4 with 10. 4 is less than 10 and 10 does not have a left child, so you add 4 right here. Okay, so that's how you fill. That's how you fill the binary search tree. That's how you fill the binary search tree. So this is the complete binary search tree for this example. That's it for the day. Thank you very much.